This lesson is about alcohols. Alcohols are organic compounds that contain a hydroxyl group, or an OH functional group. Naming alcohols follows many of the same steps we've already learned for naming other kinds of organic molecules. As usual, our first step is to identify the longest chain containing the hydroxyl group, and that's the OH group. So the longest chain needs to include the carbon that the OH attaches to. We then name the parent chain, and the root is going to be our little Greek word that indicates the number of carbons in the chain, and our ending for alcohols is all. Alcohol, all. For instance, the 2-carbon chain is eth, and our ending all, so the 2-carbon alcohol found in alcoholic beverages is ethanol. We then number the main chain so that the hydroxyl group receives the lowest possible number, just like we did with many of our other kinds of organic molecules. And again, if there's more than one alcohol group, more than one hydroxyl OH, we need to indicate that with our di or tri prefix. We then name and number any other substituents as we usually would. Alright, here are some beautifully drawn alcohols, so let's name them. Our first step says that we need to find the longest carbon chain that also contains the hydroxyl group. So we can see here our hydroxyl group is attached to this carbon, so this carbon must be in the parent chain. So the longest carbon chain, 1, 2, 3, 4, 5, 6, is longer than 1, 2, 3, 4. 6 carbons, of course, is hex, and we have only one alcohol group to worry about, so no prefix is needed here. So it is hexane 1-all because we have numbered it so that the hydroxyl group gets priority. We also have a methyl group on carbon 3, so we are going to add 3-methyl and get 3-methyl hexane 1-all. You'll notice that this example here has more than one alcohol. So it's a polyalcohol, and we have to indicate the position of each hydroxyl group. So we can see that we have a 1, 2, 3 carbon chain, so that is going to be propane. And we have to number our carbon chain. In this case, we can number it either way, and it will turn out the same. 1, 2, 3, and we need to indicate the position of each alcohol. So we have propane, 1, 2, 3, triol. Now you may recognize this structure here as being the aromatic hydrocarbon benzene. Now aromatic hydrocarbons, like other hydrocarbons, can have a bonded OH group, and in this case it forms an aromatic alcohol. This is the simplest aromatic alcohol. It's a benzene ring with one hydroxyl group, and its IUPAC name is phenol. That's an H, sorry. Phenol, just like when benzene was a substituent, we called it phenyl. It's the same root. So one hydroxyl group on a benzene ring is called phenol. All right, let's try drawing some alcohols. So we first look at the root to see how many carbons are in the chain. In this case, it's butane. Butane is 4 carbons long. And we can see that it has 2 alcohol groups at carbons 1 and 3. So if we number our carbons, we can see that our hydroxyl groups are going to be found here and here. The positions indicated by the numbers. It's of course an alcohol because of the all ending. Filling in my hydrogens for a full structural diagram there, we have butane 1,3-diol. So here, if we find the name of our parent chain hidden there in the middle, hexane, so that is indicating a 6-carbon chain. Of course, we know it's an alcohol because of the all ending, and that hydroxyl group is going to be found on carbon 2. Now we have substituents, methyl, so we have substituents of 1 carbon in length, and we have 2 of them, indicated by the di prefix, and they are at carbons 3 and 4. the correct number of hydrogens so that each carbon is bonded to 4 things, and we have 3,4-dimethyl hexane-2-ol. So one other thing to know about alcohols is that they can be classified as primary, secondary, or tertiary. And that is just indicating how many carbons the carbon with the hydroxyl group is attached to. If we look at the carbon attached to the hydroxyl group, we can see that it's only bonded to one other carbon. So we call this a primary alcohol. However, if we look at this alcohol over here, we can see that the carbon that has the hydroxyl group attached to it is bonded to 2 other carbons, one here and one here. So we call this a secondary alcohol. The carbon with the hydroxyl group is attached to 2 other carbons. Now you can see with this alcohol here, the carbon bearing the hydroxyl group is bonded to 3 other carbons. So we call this a tertiary alcohol. Now, whether or not an alcohol is primary and secondary or tertiary will come into play a little bit later, and because it dictates the types of products that can be formed in certain reactions. An important property of alcohols is that the hydroxyl group is very polar. We know that from last unit with the electronegativity difference between the hydrogen and the oxygen. This is different to alkanes, who only have carbon-hydrogen bonds and are very nonpolar. This means that small alcohols are polar and miscible with water. That's because the hydroxyl group, the polarity of the hydroxyl group overpowers the non-polarity of the small hydrocarbon group and allows it to be soluble with water. The longer chains, however, longer chain alcohols are nonpolar, and they become more and more nonpolar as the length of the chain increases. And that's because the nonpolar hydrocarbon portion of the molecule starts to overpower the polarity of the hydroxyl group. And we should know from last unit, looking at the hydroxyl group, that alcohols are capable of hydrogen bonding with each other. And if we remember, this is a strong intermolecular force and causes the melting points and boiling points of alcohols to be higher than an alkane of an equivalent length. So for example, ethanol, with its hydrogen bonding capacity, would have a higher melting boiling point than ethane. So now we're going to look at a few of the reactions, the organic reactions involving alcohols, a few of which should seem familiar to you. So we talked a bit about hydration reactions before, we just didn't know how to name the products. And this is the preparation of alcohols from alkenes. So we're adding an OH group onto a double bond. So for example, if we take an organic alkene like butene and add water in the presence of concentrated sulfuric acid, this is, of course, an addition reaction. We're adding a small molecule across a double bond. The OH portion of the water is going to add to this carbon, and the hydrogen is going to add to this carbon, and the double bond is going to break open to accommodate that. Now remember, the hydrogen could have added to carbon 1 or carbon 2, but we chose to add the hydrogen to carbon 1 because of Markovnikov's rule. Carbon 1 already has more hydrogens bonded to it than carbon 2, so the rich get richer and the hydrogen goes to carbon 1. So we end up with butene-2-ol. Now I've drawn it out like this so you can see that the one hydrogen that was attached to carbon 2 is still there, and the 2 hydrogens that were attached to carbon 1 are still there. We've just lost that double bond in favor of adding on our small molecule, adding our hydrogen onto carbon 1 and our hydroxyl group onto carbon 2. So complete combustion of alcohols is very similar to the complete combustion of hydrocarbons. Propan-1-ol here is going to combust into carbon dioxide and water. So we saw elimination reactions previously with haloalkanes or alkyl halides, and it's the same concept with alcohols. We're going to eliminate our alcohol as a molecule of water and form an alkene. Now our organic molecule here is again propan-1-ol, and in order for this elimination reaction to go forward, we need to heat it. The triangle is the symbol for heat. We need to heat it in the presence of concentrated sulfuric acid, and this will let us lose that molecule of water and will form a double bond in its place. So following the same guidelines as alkyl halides, we've lost our hydrogen off of the carbon that is bonded to the most other carbons. In this case, it was our only option here. So we've lost this as a molecule of water and formed prop-1-ene. Now, because you're losing a molecule of water, you may also see this reaction referred to as a dehydration reaction.